Welcome back. Our next speaker will be Dr. Mila Pandurovic, Associate Research Professor at the Vinci Institute of Nuclear Sciences. She navigates the impactful integration of data science within high-energy physics experiments. In this insightful presentation, she sheds light on the critical role data science plays in deciphering complex particles like the Higgs boson. Through her expertise, she explores the challenges posed by immense data volumes from experiments like the Large Hadron Collider and upcoming Collider projects. Dr. Pandurovic offers a captivating glimpse into the realm of precision amidst formidable background noise, emphasizing the significance of economic data science in unraveling the secrets of our universe. The title of Mila's talk is Data Science in High-Energy Physics. Ms. Pandurovic, please come here, join us.
Thank you. Thank you. Good morning. My name is Mila Pandurovic, as I heard, and I'm Research Associate Professor in the Vinci Institute of Nuclear Sciences. And today I will go tell you about the data science and high-energy physics. Now, I must say that it was a challenging task to compress all the information about these topics, the synergy between these two topics, into this half an hour. Actually, I heard now 25 minutes. Okay, so I hope that you will, at the end of the talk, you will have the global view of the level of involvement of data science and our high-energy physics. Okay, and I hope you will enjoy it. So, where do we start? You may have heard of, about 10 years ago, about the greatest discovery in physics, which was the discovery of the Higgs boson. Now, this discovery brought an actual Nobel Prize to two gentlemen, Peter Higgs and Francois Englert, and this discovery actually was more than that. It was a triumph of the standard model of the particle physics, which is a theory that explains elementary particles and interactions between them. Now, this Higgs boson here at the end, which you see, is completing the standard model. So now we have 12 particles, 6 leptons and 6 quarks, and 3 out of 4 forces are actually incorporated in the standard model. Okay? So gravity, strangely enough, is not included yet. So the Higgs boson and this discovery actually shed the light and explained the origin of mass of elementary particles, which is, of course, in everyday life a normal situation. But in particle physics, origin of mass was a mystery. So how do actual particles, elementary particles, gain mass? By the interaction with this Higgs boson. Okay? So what's that got to do with data science? And you will see just about everything. So let me show you the world's greatest or the largest, and for that matter, the most expensive experiment in the world, which is the Large Hadron Collider. It is located and built under Geneva and part of France, and it's nested in the 27-kilometer ring, and it collides 2 proton beams at the energy of 13 tera-electron volts. Now, this collision happens every 25 nanoseconds. So 9 experiments are hosted by the LHC, and 7 of them are actually dealing with a small part of physics. And 2 of them, Atlas and CMS, which were actually in charge for the great discoveries like the Higgs boson. Actually, the Higgs boson was discovered by Atlas and CMS simultaneously. Okay, it was said, and it was calculated, that these collisions, which are produced by the LHC, actually produce 1 petabyte of data on these experiments every second. Okay, so that's a lot of data, and that calls for data science, of course. Now let me show you about a bit of detectors. So here you see the CMS, one of the detectors, and this is during the shutdown, so we can see inside a bit. So these detectors are approximately 10 or 15 meters by 12 meters and large. So we wanted, and they're discovered they are designed for the complete detection of the proton-proton collision. So the question is, why do we need such a big detector for detecting the collision of 2 protons? And the answer is, we have an enormous amount of energy, which is 13 TeV, which is inserted into this collision. Okay? So when you insert that amount of energy, that energy is then converted to the mass of converted particles. So we have the masses, which is created by the E energy equals to mc squared. The mass of the particles, which are 100 times greater than the mass of the protons themselves. So each of these particles are also highly energetic, and of course they decay. So each class of particles, they want each separate detector. So, for example, like electrons and gammas, they want electromagnetic colorimeter, and further hadrons want hadronic colorimeter. So our detector is like a sausage, which is wrapped around with many layers of detectors. So we start with the vertex detector, and then tracker, electromagnetic colorimeter, and so on and so on. Because we want nothing to escape, we of course stuff the back and front of the detector with the similar structures of detectors themselves. Okay, now every and each of these sub-detectors are actually highly pixelated, okay, with their own readout. So what happens when collision happens? We have fragments scattering around, millions of fragments in there. So they hit the detector, they leave hits, and from those hits, we have to reconstruct our event. Okay, so lots of data handling. We have to do here is like first we have to collect the data and then trigger and then reject or store. After that, you're going to see the cleaning of the data and so on and so on. Now, the LHC has been running for around 7 to 8 years. And in this time, lots of results and lots of discoveries, small discoveries, were made. One big discovery, as you heard at the beginning, the discovery of the Higgs boson, and one Nobel Prize. But after that, no new discoveries. That means no new physics. Okay? So for all the viable theories that we're testing from beyond standard model, we actually get the limits. For what the limits means, been there, done that, no new physics, looks elsewhere. So these are only the part of analysis that were done on the LHC, actually only in Atlas. So many other theories were tested on the CMS and all other experiments at the LHC. Now, beside the new physics, what we want to do is precision physics. Okay, so we want precisely to measure the properties of particles, standard model particles, and also composite particles. So for exactly, we want to measure the mass, the couplings, and the cross sections. Okay, so just as an illustration, just Atlas and CMS published more than 2,000 papers over the course of 7 years, and which all contained many analyses in them. So lots of analysis, lots of results, lots of papers. And these are, of course, peer-reviewed papers. I'm not talking about conferences. Okay? So let me see what we are with our LHC. So LHC actually has been running since 2009. But from 2011, we've held really high energy from 7 TeV. And we have runs and following by the long shutdowns in which we upgrade the detectors. Okay, currently, we're here at the run 3, okay, which will last 3 more years. After that, we have a long shutdown, and we will upgrade the detector fully. So that will call the high luminosity LHC, which will in the end, and which will run until 2040. Now, let's start from the beginning. Actually, we started backwards from the discovery and from the Nobel Prize, but how does it all begin? Okay, so we observe some phenomena. We try to fit it in the standard model. We can't. Then we have to find out some other explanation for it, and that's where theories come into play. And they actually take the take the theory, which is a quantum field theory, and try not to overstep the current laws of physics. And they come up with very imaginative, funny theories which explain these models and the models. So from this, when our scientific community agrees on the priority of topics and on there is enough of these theories that we can test on the next machine, then we want to design new machine. Okay, so that's where we go into our R&D. Okay, so R&D phase in there for next collider, what we want to do is we want to design the detector and the accelerator, and we want to prove by the simulation that we're able to see by using such and such detector and such accelerator that we are able to see the processes of interest with enough statistics that we can actually declare discovery. So how do we do that? The first step is to integrate the standard model processes and the new processes that we want to test into Monte Carlo event generator. Then we generate lots of data from there, and we go to, in parallel, we're developing the detector. We're Gen 4 simulation. So what we do is we insert this data into our simulation of a detector, and we obtain, again, hits from which we want to reconstruct our event. The result of this phase is going to be the relative statistical precision with which we can measure in certain fields, like the Higgs field. And if that is below the limit that is required by the theories, that means that we're OK, and then we can proceed to the next level. After this, what we do is actually go to the physics boards in order to get approval from CERN and from DAISY and from so on, the great big laboratories. And after that, if we're lucky enough and get approval from them, we go to our finances, and maybe we're going to get a new machine in physics. OK. So after that, we come to the building phase and the running phase, which we already saw. Now, what we want from our new machine? Of course, we want to go high in energy. Why? Because high in energy means you're digging deeper into the structure of matter. Here you see the history of the colliders, and you see that energy is slowly rising. But you can also see that there is an interchange between the hadronic machines and the electronic machines. Hadron machines we are currently having the LHC, which collides two protons. And before that was LEP, which collided electron positron. And the next machine is going to also be the electron positron collider. OK, so, but more energy, of course, more data. So the other thing is what we want to do is have more statistics. What happens is, if you haven't have enough in energy, and you actually can reach some phenomena, if you don't have enough statistics, your signal, of course, is going to be buried under the pile of background. So you want to have enough statistics. Right, so I'm going to illustrate that in two examples. The first one is the discovery of the Higgs boson. So in 2011, they declared a hump in the data, right? So, but they cannot say that it's discovery. We had to wait. So we waited, time passed. More and more data flew in, the hump was rising, and finally in June or July, I can't remember, we declared discovery. Okay, but another example was a funny one. In 2015, again, they observed a hump at 750 GeV. Okay, so by the time that was published in the news, around 30 days from that, 150 papers were actually published, theoretical papers, which explained this phenomenon, hump on 750, were published on the archive. Okay, so time passed by, data flew in again, the hump disappeared, so no discovery. Okay, so that's why we need more energy and more luminosity. Now, next machine is going to be the Electron Positron Collider, as declared by European Strategy Update from 2020. Okay, so 4 concepts are developed in parallel. We have 2 linear options and 2 circular ones. And with no preference, here we have at the top 2 European ones, which are developed by CERN, Compact Linear Collider CLIC, and Future Circular Collider FCC. Now, of course, the Japanese are, of course, planning one, which is the Linear Collider, ILC, and the Chinese, which are planning to do the CEPC, Circular Electron Positron Collider. Now, let me just state that LHC is 27-kilometer ring, and the CLIC is planned to be 50 kilometers long machine, and the FCC and the CEPC from 86 kilometers circumference to 100 kilometers circumference. So that's a major upgrade. Now, let us see the timeline for these 4 machines. All these machines actually, to develop this such a complex machine, of course, you need to start at least 15 to 20 years before you want your first run. So all the machines started earlier. So we are already finished with all R&Ds for these machines. And for all machines, the first run is planned and hoped for around 2035 or 2040. Now, which one of these machines are going to be built, or how many of them are going to be built, we still don't know, because none of them got approval, full approval yet. Okay, so whatever happens, for our physics, it's all the same. Why? Because we're aiming for physics, okay? We don't care where do we do it, we're just going to do it. So the three basic pillars of our physics case of any future collider are the Higgs boson physics, the top quark physics, and beyond standard model physics. So Higgs physics is the priority of the any future collider. So what do we want to do with Higgs physics? We want to measure precisely the properties of Higgs boson, so the mass, the couplings, and the cross-sections. Okay, so I'm going to present one of the analyses that was performed for the ILC and the CLIC, and finally by the invitation for the CEPC, for Chinese CEPC. Okay, so here we have the data flow of a Chinese CEPC Electron Positron Collider. So again, I have to show this because, again, we have the physics models, which are incorporated in the Monte Carlo generator. For that, on CEPC, we use some wizard event generator. We did the fragmentation, the famous Pythia fragmentator. And then we inserted that into detector simulation, CEPC ILD model, right. Then we obtained hits. After that, we have to do the track reconstruction. Okay, here are all the models which are helping us to reconstruct our events, actually to reconstruct our tracks. And the end of this phase is actually you have tracks, you have particle IDs, you have energies, masses, charges, and everything connected to these particles. And this is actually where the analysis actually starts. So this is the analysis that I want to show, just an example of how we do it. So this is an analysis of Higgs boson decay to a pair of W's. You see that in the end pictorially. And because this is Higgs produced and the Higgs-Strong process, we have, again, one Z boson at the end. So we have three bosons, and we want them to decay hadronically. What does that mean? To decay to a pair of quarks. Okay, so quarks are very peculiar objects, and you're going to find out what the quarks do, actually, in the next slide. So quark decays to jets. So we have very complex 6-jet signature here, and we want to reconstruct the event, and we want to finish up with the relative statistical uncertainty of this process in order to say whether we can measure it on CEPC or not. So jets are very peculiar objects. So what happens is when some objects want to decay to quarks, actually it can't, because there is a property called color confinement, which actually forbids the quarks to decay into physical objects. So what the quarks want to do is he's covered up, he actually creates many colored particles, so at the end he remains color neutral, and that way he can decay only. But it doesn't decay like in a ball, like a spherically, like isotropically, but it decays like in a conical shape, okay, the conical formation, which is like a spray of particles. And that spray of particles are called jets, okay? So this is the illustration of a jet formation. So first here you have this part which is called hadronization, where the quark actually puts up the another particles around him, and then you have fragmentation after that. So imagine we have 6 of those jets to reconstruct in a single final stage. So we have to do first the tracks. Track reconstruction is done by collecting all the hits from all the information from the detectors, subdetectors, and creating the tracks, most probable tracks of the particle. Now, at the beginning of the story, I told you that every class of particle needs its own detector. So photons and electrons, they need electromagnetic calorimeter, the red one on the figure. And our hadrons, which is the product of decay of quarks, actually need hadronic calorimeter, which is the green one. So imagine this wood upstairs creating the cascades further and calorimeter. So those are hits which we want to convert to tracks. So CEPC reconstruction software is doing a good job. And you can see just pictorially what it does. It takes the graphs and the other objects. So after this, oh, I forgot to tell you. besides the physics collision of the E plus E minus and forming some physical event, we have something called machine background. Machine background is actually, because when the protons and electrons, when the electrons and positons collide, they actually emit gammas. So those gammas interact, and they create further particles which actually cover up our signal. So most of the, all detectors and all projects actually came up with a software that actually removes and cleans the event from the machine background. So this is actually not on CEPC. This is, I took it for CLIC because it has a nice pictorial representation what happens before and after. So this is our event covered up in machine background, and we have to clean it and get something like this. This is our actual physical event from we want to reconstruct that one. Okay, this is just analysis flow, what we do in analysis here. First, we want to take all the tracks and force them to become jets, okay? So that's forcing them to become 6 jets in this case. After that, we want to do a vertexing. Vertexing means find the exact position of the collision of electrons and protons, electrons and positrons. After that, we fully reconstruct our event, and we do that procedure also for the background with the same parameters. Then we want to separate our signal and background. We do the pre-selection and multivariate analysis. In this case, we did BDT, boosted decision tree. And finally, the result of this analysis is supposed to be relative statistical uncertainty. And we can tell whether this process is measurable at CEPC. Now we come to our jet reconstruction and our event reconstruction finally. So as I said, we force events into 6 jets. Then we want to pair them in order to produce the 3 bosons that we started at the beginning. Those 3 bosons are 2 Ws, and they're going to create our Higgs. So we do a set of iterations of optimization, first of a jet opening, and then of jet combinations, okay? And the final combination that we want to obtain is having the minimal chi-square test here, given here, and the minimal error between the reconstructed invariant boson masses of Z and invariant Higgs mass. So in this series of optimizations, we obtained our result. And this is the result which I was very happy about. This is the reconstructed invariant masses of Z boson, Higgs, and invariant masses of W. Okay, so with the same procedure and the same parameters, we do that to all the backgrounds that we have. Now, this is the list of backgrounds that we use, and this is only the dangerous ones. All other backgrounds, actually, we could get rid of at the level of preselection, so they are not important. These type of backgrounds can actually mimic our signal, as you are going to see in a few seconds. So, and they're at least up to 3 orders of magnitude higher than our signal, the number of events. So what we want to do after the reconstruction, we want to find features from which we can actually distinguish our signal from background. So in the case of hadronic final states, we do not have any sharp tagging variables, like in case for leptonic final states, those are the objects that do not decay. So if you have 6 leptons, then you end up with 6 leptons in the detector. That's not the case for hadronic, so we have to use all the tools that we need. So we use kinematics, we use topology, energy, and jet reconstruction procedure, and so on and so on. Without going into details and physics of this, I'm just going to show you several variables which you can visibly see that they're effective. And here you have the invariant masses, which we reconstructed for our signal, which is given to the black, and all the just important backgrounds. And as you can see, the Higgs, which is given in the black, has approximately the same shape for many of the backgrounds, okay? So, and as well as the W. So these 2 actually invariant masses are not very efficient at all. But the invariant mass of the Z boson is proven to be efficient, okay? As you can see, the most of the background is actually have a different shapes than the invariant mass of the signal. Besides that, the most effective one is the shape of the event. What does it mean, shape of the event? How does it actually look like in 3D? Okay, so our signal has, because it has 6 jets in the final state, many particles emerging, is actually spherically located, while some backgrounds, like a 2-Fermi background, are more like pencil-like. So this variable, which is called the thrust, is actually serving us to distinguish the best variable for distinguish a single background. Now, we can use also energy and topology, and it was proven to be a good variable. And besides that, we can use just plain simple counting of final state particles in the detector. Okay, so because we have 6 jets in the final state, that means that we have more and more particles in the detector than the, for example, 2-jet final state. So at the end, let me just show you what we did with the BDT and the preselection. So most of the backgrounds are actually reduced to the % or some % level. Okay, so in total, we reduced 99% of this difficult background. And when we counted all the backgrounds that they started from, 99 and then 4 nines after that. Very high efficiency reducing. But let me just show you the 2 tools that we used during the analysis. And these are the tools which can actually be used outside the high energy physics, very useful tools. And this is for data analysis and the visual presentation of the measurement of the results. And it's CERN-developed software. It's a freeware, and you can download it from the CERN site. And it was developed by also fellow physicist René Brun. So you can get, for this software, you can get lots of support from the creator and also from the root forum. Another tool that we used at this analysis is TMVA, Toolkit for Multivariate Analysis, which is also root integrated, but you can also get it as the single one. So it contains, as you see, many machine learning methods, and it's a very useful tool. And for that also, it's also freeware. For that also, you can get lots of support from forums and lots of support from creators. Okay, so from this, we use the BDT, boosted decision tree, for our separation of our signal and the background. Now, let me just say that all of the, most of the calculations were done on the grid. So this is not actually publicly available, but it helps us to speed up, that's very high computing, helps us to speed up the processes of calculation. Now, let us come to finally our signal and background. So this is our final result. The first one is after the pre-selection, so we cut the majority of this unimportant background. And at the end, we're left with this. So our signal is with black, so we see that it's still under lots of background. But when we calculate relative statistical uncertainty of this measurement, we see that we can measure this process with a very high precision, okay? And this process actually passed, and it entered the global Higgs community paper. So here you see we investigate all Higgs decay modes, and we have proven that at the CEPC we're able actually to see all the relevant Higgs decay processes with statistics that is desirable. Okay, so this actually paper went into the funding agency for the approval. That didn't get approval yet. So, as you can see down there, we have all the results from all the future colliders, as well as the high luminosity LHC, which could prove with many results obtained here that, for example, Higgs physics is feasible on the future colliders. Okay. So that brings me to my summary. Okay, experimental high energy physics is a data science, definitely. And let's go back to the Higgs boson from the beginning. Okay, so Higgs boson in the beginning is the particle that gives the mass to any other particle. So if someone asks you, or ask us next time, did we gain weight? We can actually say, no, it's just Higgs sticking to me. So thank you for the attention, and that's it.
Thank you very much. Do we have questions? Yes, please. Just a microphone. Just a second, please. Mm-hmm.
Thank you for the presentation. I know doing data and physics presentation 30 minutes is extremely hard to go to theory, experiment, and talking about everything. My question is, right now, physicists, we are doing work all alone in our homes, and we are making simulations for bigger colliders, bigger interferometers, and there is a limit. There is a limit in capability of what we can do and the time we have to do these things. And my question is, in your experience with physicists' work, what do you expect data and AI to help us in not only cutting this time short, but actually changing the way we think about doing research, and not adding more masses to the standard model and more, and having to review a new paper each week that says that they got a new parameter to discover a new small, how do we say in English, intersect between particles. So for me, the puzzling is what's the limit? What's beyond this, and how can we use AI and data to make it?
Okay, let me just make it clear. What's beyond what? What do you mean? What's beyond the?
Beyond the way of just adding more parameters to the standard model.
Oh, the standard model.
Yeah.
Okay. Okay. Actually, that's a personal question and personal preference. The standard model, let's say, for example, adding more parameters, then you go into SUSY. Personally, I don't like it, but many limits actually are tried to, the SUSY is being cut down. But there are other theories that actually do not add parameters. They add, let's say, for example, extra dimensions. They add extra dimension. Personally, I'm not in favor of that also, but I'm not going to say my preference. So as adding more parameters to standard model, actually, myself personally, I don't believe in it. Actually, it's getting more and more complicated. It's like building on the sand, okay, to me. But as use of IE, I can see it's very useful, especially, I said, in the processes of reconstruction, okay? Because here we have much problems, and that's data consuming and time consuming. Okay, so it would be nice to have the IE help us with that and to reconstruct our objects better and bigger. So that way we can do the analysis in much more relaxed way. Okay, does that answer your question?
For an hour, but yes.
We can do it afterwards.
Okay, thank you very much. That's for now. That's for you. Thank you.